When two chords of a circle intersect, the product of the lengths of it now. There's two possible diagrams, but let's write the words first. When two chords of a circle intersect, the product of the lengths of the intervals I'm going to write it without the little inserted bits. Oh no, it's the next one they put the inserted bits in. The product of the lengths of the intervals on product of the lengths of the intervals on one chord equals the product of the lengths of the intervals of the that was messy. Intervals on the other chord and then they just go and its converse. Which is very cryptic indeed. And I don't think the textbook proves the converse. And I don't think I'm going to bother either. That was a lot to write. You can look at that if you'd rather, Shannon, rather than my writing.
No, it's not your writing. It's making sure I'm not repeating myself.
Yeah, correct. That's why I look carefully several times. When two chords of a circle intersect, the product of the lengths of the intervals on one chord equals the product of the lengths of the intervals on the other chord, and its converse. There are two possible diagrams because the chords might intersect in the circle, or the chords might intersect, that wasn't a circle, outside the circle. More like a fish than a circle. Not to worry. We'll pretend. A, B, C, D, E. A, B, C, D, E. Chords might meet inside or outside. When it's outside, you've got to be careful how you interpret it. Okay. What is the theorem telling me? The theorem says the product of the lengths of the intervals on one chord, this times that, has to equal the product of the lengths on the other chord, this times that. But when it's outside, you must be careful. Because we're talking about the intervals from the point of intersection. Of course they're mowing outside today. So we're talking about this and that, and this and that. Very common error, and I have seen it happen on the usual any kind of question I put in there on IA2 is to go this times this. Not correct. This times that. So we're trying to prove, required to prove that AB, no, I'm going to do it differently. Did they go AE or EA? Let's do it the same way they did. EA, okay. EA times EB equals EC times ED. Not EB times BA or ED times DC. We're always measuring the intervals from the point of intersection. That's important. Okay, let's look at the first case. A, E, B, C, D. What can I say for sure? Let me draw, now it doesn't really matter, but I want to do it the same way they did. A, B, C, D. I'm going to go this one and this one as additional lines. What can I say? The angle CEB is the same as the angle AED. Do you agree with that? Because they're vertically opposite angles. They must be equal. But we can say more. This arc subtends here and here. So these two angles must be equal. Angle CBA must be the same as angle CDA. Arc, no, I don't know how to write that. Subtended by same arc. Sorry, I'm standing in the way. Subtended by same arc. So these two angles must be equal.
So we do the same thing for the other one?
And the same on the other side. This arc subtends this one and that one. So therefore, let me get this right. BCD must equal BAD. Same arc again. So if those two triangles have three angles the same as each other, then those two triangles must be
similar.
Don't leave Eddie to answer every time, people. Come on. Therefore, triangle, got to get the order right to get the, so we'll start with E, B, C must equal, is similar to triangle EDA. Angle, angle, angle. EBC is similar to EDA. They're flipped over, but that's okay. They're similar, they've got the same angles. Why do I want to say that? Because if I write this down correctly, EC over What do I really want to show? EC over, I think it's EB. Does that sound like what I want to write? Okay. Oh, they did it the other way, it doesn't matter. EC over EB. Oh, you want to go one triangle to the other? EC over EA, let's do that. EA must be EB over ED. Because they're similar, corresponding sides have the same ratio. That's what similar means. There's a consistent scale factor from one to the other. Now cross multiply and you should get this. I'm going to get EC, ED has to equal E, right at the same order we had up there, EB. If the triangles are similar, corresponding sides, would it help if I highlighted those corresponding sides in two different colours? So EC on EA has to equal EB on ED, because those are corresponding sides. So far so good. I can show that it's true when they meet inside the circle. What about when they meet outside the circle? A, B, C, D, E. Of course they use a different letter, why not? Get this right. Oh yes, okay. So now we're going to draw two different triangles. Pick another colour. This triangle and this triangle. I want you to consider triangle ADE and triangle ADE and CBE. And you see those two triangles. Not the ones inside, there's one here and one here. Obviously, they have this angle in common. So, AED is CEB. They're the same angle. They're exactly the same angle. Now, think about this angle and this angle. What can you say about these two angles? They're the same, because they're on the same arc. So, EAD has to equal ECB. Same arc. EAD, ECB. And what can you say about these angles? Wait, which angle do I actually want now? I want this angle and this angle. That's what I really want. I like the interior ones. Well, that's harder, but I can say these ones are equal, right? But if they're equal, then the supplementary angle on the lines must also be equal. If these two are equal, then these two must also be equal. So angle A, how am I going to get that right? I want to go, and this triangle, I'm going to go this angle. ADC has to equal, ADC has to equal CBA, same arc, and therefore the ones I actually want, ADE must equal angle CBE. Hardest bit here is getting the right letters in the right places. Why did I do all that? Because now I've got two similar triangles, and I'm going to use exactly the same argument. Therefore, triangle ADE is similar to triangle CBE. So, sorry, angle, angle, angle. Which means, what did I use last time? Red and orange. Which means I want EA, EC, and EA. See how I'm getting the whole length out of this triangle? And the other ones are going to be BE, yes, and DE. They're in different spots, but they're the same labels. Because unlike the textbook, I labelled them with the same letters. Therefore, EC over EA has to equal, EC has to correspond to EB on EB. And the result will follow. ECED has to equal EA, EB, and I've proven it both ways. No, I haven't. No, I haven't. I've proven it for both cases. What I haven't proven is the converse. What does the converse even mean? So the converse says, if I don't have the circle, I've just got two crossing over lines and 4 points on those lines such that this is true. The product of the intervals on one length, on one side equals the product of the lengths on the other line segment. Then those four points are on a circle. You can draw a circle around those 4 points, just touching them. I'm not going to attempt to prove it. It's the same kind of reasoning.